there? Perfect. All right. Hey, my introduction has already happened, and a lot of family members are also here, so they know me very well. I have got an opportunity to build a distributed or decentralized finance or a blockchain platform as an architect. And with that, whatever I learned, my experiences, I'll share. With a lot of things I cannot talk about it. There are some restrictions to what I can reveal and what I cannot. So I will be revealing whatever is okay to do that. Hope I give you a good depth in how these kind of platforms can be built or these kind of networks can be built. Anil has given a very good walkthrough on the entire space, how does it work, how many systems put together work, and this entire DeFi ecosystem, the kind of use cases they are coming through. But when it comes to technology, banking is always there for these things to work. And when we talk about banking, there's always this question, does it have ability? And I don't say that, people say that, so don't put me into that spot. I said that. So people say that banking is slow in adoption and a lot of bureaucracy there because of that kind of an organization. It's hard to build new technologies, to bring new kind of advancements there. And, but that is that true? Let's quickly see. We have already seen what Anil has talked about. There was one point of time long ago, I come from those days, I've seen that banking when physical ledgers were used in bank branches. You go to your branch, a ledger will be brought out, a transaction is written on that ledger, a double entry is done, the transfer from one account to the other account. So double entry is made. The balances are calculated and written right there. So that is the physical ledger world that we have seen. And from there, around 90s, late 90s, online banking started. With online banking, we could do very little in the beginning, but then later it started improving. And then we saw ATMs. ATMs also, you could do only with your bank. If you had an account in SBI, you could use ATM of SBI, not anywhere else. And then the cross-banking, cross-banks, that networking started. After that, online account opening came. During COVID times, you would have seen, if you wanted to open an account, you could just you need not go to bank. You could do it all online, sitting at home, open a new account, and start transacting with it. And then we also saw the wallets and UPI started becoming very popular and being used. And then we have seen the direct benefits transfer happening. Like millions of transactions taking place together. And that was the DBT. You click one button and so many transactions happen together in one shot. And then finally, what we have just heard about, the CBDC, which is a distributed ledger technology-based currency, which has also finally landed in India and several other places. So all these things, yeah, there are challenges. Banking is a bit slow. We can say that because everybody depends on it. There are challenges. We cannot just throw away what we have and jump onto something new. So it takes time to transition from one place to other. But cryptos kind are definitely not feasible, and especially, let's say, for India, it's not feasible. And main reasons, if you see, is we've already seen accountability is very low. So if somebody steals your assets, you cannot go to anybody and talk about it. You cannot go to anybody and report about it, and there is no one who can actually come and do anything about it. The currency is free. It doesn't have any central bank involvement, so that problem we've already discussed. And because of this decentralization, and since it is decentralized, it's permissionless. Permissionless, anybody can enter the network. A lot of security has to be taken care of. And any security needs, when you try to cover for them, it takes a lot of time in transactions, and transactions become slow. When transactions become slow, you can't only do this much. So the actual transactions per second that you can get out of such networks is little, it's not much. And just to give an example, Bitcoin, they form a block of transactions every 10 minutes, if I'm not wrong. Yeah, so it's very slow. So a block of transactions is formed after every such big cycle. Similarly, Ethereum also, if we see, Ethereum has brought it down to something like 10 seconds, but still it's very high. I mean, you can't form so many transactions every 10 seconds. In 10 seconds, India is doing millions of transactions, right? The other problem that you see is, this is not just one-off thing that you can build in one platform or one network and everything starts working together. There are a lot of other systems which need to integrate with it. And any of the blockchain platforms that we see, they work in their own box. They do not see anything outside. So everything has to be coded within that. Any functionality that you need to build within that. But the world that we have grown, we have seen integrations so far. You want to build any functionality, any special functionality, you create a new service for that. Any other functionality, you create a new service for that. Microservices, right? So we have seen that kind of an architecture so far, and suddenly an architecture where it says, no, you put everything together into one box, it's not going to work. And regulations is an anti-pattern there. Nobody likes it in that world, but it's a pattern for us. So these are the problems which kind of hold us from directly adopting to what we see in general in the DLT framework. But then, apart from that, there are some good features as well that we need to look at from technical standpoint. Tamper-proof, immutable records, Anil talked about. Anywhere you go, I have built many platforms with banking, in credit card space, and insurance space. One thing happens with it. How many developers are here? If you can just raise hands, so I get. And how many of you? Okay, just keep your hands up. Just keep your hands up for a moment, please, just for me. And how many of you have actually handled production systems? Rest of the people can bring their hands down. Okay, so enough number of people who have handled production systems. Now I could go further, production systems of enterprises. How many people have handled enterprises production systems? Okay, few. Fine. Now, all of us have gone through one problem. Things do not run perfectly in production. Something always happens, no matter what we do, right? What do we do then? Somebody will come to us, hey, you go and fix it. What do? We go to database. Sometimes some accesses are required. There is some auditing as well, but you get to go to database and try to fix something, and somehow get things working and going from that point onwards. Start a few services and get it working, right? But all of that is clearly telling it's not tamper-proof. If you can go to database, no matter with what access, and change a record, immediately the trust is gone. Because there is somebody who can go and do that, right? So that's a big problem. The second is the autopilot mode, where all these DLTs work, and that is the most important factor. One quick example, you would have seen banks have different kind of arrangements to give loans. I'll just say different kind of arrangements for street vendors and different kind of arrangements for, enterprise, organizational, and those kind of owners and stakeholders. So there are different kinds of arrangements to give loans. All of this is happening because there is no code base which is running it. We developers have not written that code base that is running it. The problem is there's somebody who's sitting, who has authority, who can go and tweak the system to get things going. And that's where the problem is, that it is not in autopilot mode. Everything is manually driven, human driven. The next thing is cryptographic security. How many of us have heard about cryptography? Okay. How many of us have used digital signatures? Okay. How many of us have used physical signatures on documents ever? Because somebody asked to do that? Yeah, many. So the thing is, let's say if you go for a loan, if you seek a loan, you go to bank and say that, hey, I need a loan of 10 lakh rupees. Bank will say, where do you have account? You have account somewhere? They'll say, go back, get your 6-month statement, 1-year statement, and then come to us. You take a printout of the statement from your online banking account, right? You can take it, right? Usually banks have 1-year statement available. You take 6 months of printout, you go to that bank, and they'll just throw it away. This has no value. Then they will say, okay, go back to your bank, take these printouts, put a notary signature, put a seal on every damn page of that statement, and then come back. Right? That means there is a signature required on every page that you produce. But how come we are working in software industry, we are producing so many applications, hardly few have thought about signatures. Where are these signatures? It's all blind trust. That since there is a digital system sitting somewhere, there's an online service sitting somewhere, it is always doing correct only. But the earlier point, a database administrator can always go and tweak your record. That door is always open. Even after that door is open, you have no signatures as well, but you still trust it. But when the money has to go out, when you have to give it to somebody, you don't trust anything. You be very careful about it. And that's where the cryptographic security comes into place. It's a very important feature where you put digital signature on each and everything that you do. So whenever you have an asset, there is a signature on top of it. Whenever you have a transaction also has a signature on top of it. And let's say you could do a transaction, but that transaction was validated by somebody else. So let's say, for example, you are making a money transfer, and then money is actually validated by an anti-money laundering check via some other service. Now that service, when it does that check, has to give a response. It's all service to service talk. One service is asking AML, hey API, tell me for this transaction I can go ahead or not. AML service says 90% probability it's all good. And your service says anything above 85%, I'm going to go ahead with this. That works. But then, did you take a hold of whatever response you got from that AML check? Did you store it somewhere? Did you get a signature on top of it or not? I think those are the questions we never ask. We just move on. So that is the important thing. Next thing. All of us, all the developers would have seen this. Whenever there is a bug in production, the first thing anybody does is, hey, was there anything checked in after I tested it last time? Right? Is it true? Isn't it? Something has gone in which is unchecked, and because of which there is a bug. And how do we find out? Then we go to Git repository, we'll find out, okay, so many versions, then go to your pipeline, figure out which version was deployed in which environment, and somehow infer a relationship between code base somewhere and what would have resulted, build a theory. And then based on that theory, you try to reproduce that bug in test environment. Now you may be able to do it, but you may not be able to do it as well, because theory may be correct or may not be correct as well, right? So all those things happen because whenever there is a code change happens, we do a versioning, but that versioning has nothing to do with production environment. It is in dev environment. Everything is running in production environment, but code changes are tracked in dev environment. We have a Git repository where you do version control. Bitcoin or Ethereum, all of these platforms, they have brought in a way of versioning these code records in the same ledger where we have all of the transactions. So whenever you make a change in your functionality, let's say you have a transfer function, something changes there, this function change goes as a versioned record in the DLT itself. Now, once you have that, any transaction that is after that transaction You have very clear dependency. You know that if this transaction differs from the other transaction, there is a record in between which says the code has changed. And you cannot just do it in Git repo. Does it make sense? And the entire industry, we started with, actually the internet started with standards and specifications. www, World Wide Web, all of us know. I come from that era when www wasn't there. And then it came, like we started jumping with joy. A lot of things started happening in our life. We saw internet, Netscape came, all of that happened. Those were not platforms. Those were all networks. Internet does not work on anybody's server. Have you heard about somebody who is running internet server? That's why you're getting YouTube videos? Internet is not running on servers, but platforms run. We got into platforms because everybody wanted to create some kind of monopoly in business. Somebody wanted to create a duopoly in business. And for those ex-polys in business, all the platforms started growing. But blockchain is telling us go back to those standards and specifications. Define specs, define standards. And for you to understand, whenever you define a standard or specification, things become slow. Because you define a spec, a lot of people started using it, and if you want to change it, you need to make sure a lot of things. So for example, when we have a database table, and we want to add a new column to it, or let's say we want to replace an existing column to a new column, or we want to rename a column, what do? We do not delete the old column. We create a new column, leave the old column as is, make sure that my database change is backward compatible, and then at some point when all the data has been migrated to the new column, we'll try to drop the old column. The same philosophy happens here also. You cannot just delete something and put something back. It has to, whenever you have standards and specifications, things move a little slow, and you need to make sure that every change that you bring in after that is backward compatible, so that all the people who are using the standard are not just shut after that. So these are the features that we need to be careful about. And the most important thing, which Anil also talked about, is the programmable money. We already have it in CBDC. The wholesale, we have seen it's some programmability features are there. But programmable money is very important. Right now, whatever money we get, we don't know how to spend it. We can go and spend anywhere. So for example, is government giving a direct benefit transfer to a farmer? Now with CBDC, government can ensure that farmer can only spend that money, that token, buying fertilizer or buying specific equipments. Let's say buying a tractor. So when some money is given to buy a tractor, you can only buy a tractor. You cannot buy anything else. And that's where you kind of control a lot of poor expenses of those which should not have already happened. So all of these things actually bring trust from both parties. On the left side, if you see, these are all the trust factors which is required for the end users. On the right side, programmable money is basically bringing trust to the money giver who's giving the money. And it's a mutual trust. And wherever there's a mutual trust, we end up seeing results. Now, okay, fine, we understood the paradigm, we understood what is happening. Let's get a little more deeper into it. From tech perspective, so many developers are there, they're interested to know, okay, what did we do to build that kind of a platform? And a blockchain network that can scale massively. I already told you some of the existing platforms. No, I shouldn't say platforms, these are networks. So these networks did not have that kind of a scale. And we needed to build something, let's say, for a scale of population of India. So how do we do that? Let's see. Everybody is with me, right? We're going to talk about how a DLT works. How do these transactions actually happen? Is it visible there? Okay. So this is. So these are the applications on the left. Applications could be anything. You may be running it on your mobile device or on your laptops. But the actual DLT architecture starts from the validators and block creator there. Okay. Now, what happens is, what are validators? They are supposed to validate a transaction. So let's say you are doing a transfer. It is validating whether you have enough balance in your account or not. It is also validating where you're permitted to do that transaction or not. You're allowed to do that or not. AML checks and all those things. They are all validators' job. The block creator is the actual block creator, which will put many transactions together in a block and append it to the blockchain, which is there at the bottom. And the blockchain is your database here. So all of us know databases. This is the database. The chain is the database. Okay. So what happens is a transaction one, which starts from app and gets to the validator. Validator says, is it a valid or not? Oh yeah, it's a valid transaction. So it is passed on to a block creator. You consider them as services running together. So block creator is a service which is getting that transaction. And then that transaction is sent to the block which is ready to accept more transactions. Because every block has two ways to complete. One is by number of transactions. So many transactions have already happened in that block. So it says, okay, I'm done. Or if a time lapse has, let's say 1 second has passed, or whatever the time limit is, then also block is complete. Then another transaction comes in and it says, oh, wrong, it failed. If it fails, it goes elsewhere and we record it for audit purpose, etc. It still goes to the database. And then another transaction comes, which is valid, and finally it reaches the block. Once the block is complete, the block creator is actually pushing this block into the blockchain, and that's how the blockchain completes. Now, these block creators cannot just take that call that, okay, I have created a block and should go to blockchain. A lot happens there before it can actually say my block goes into blockchain. We'll just talk about it in a minute. But let's understand what is happening here. So these are various DLT networks that you would have seen. On the left, you can see Bitcoin is there, Ethereum is there, bottom some are there. On the right also there are some other platforms. The problem is some of the platforms who are very tightly dependent on security and decentralization. For example, Bitcoin and Ethereum, they are permissionless. They need to be fully decentralized. They cannot put any kind of permission or any preferences to any peers who can take part into that network. It has to be totally permissionless. There is some criteria defined. If I fulfill that criteria, I can be part of it. You fulfill, you can be part of it. So this is fully decentralized. On the right side, security and scalability is what is more important, where they say that, okay, decentralization is probably something we can be a little relaxed on, but I'll go more on scalability. Now, if you see, out of these three things, security, decentralization, and scalability, you need to lose one. You need to be easy on one of them. You can't get all three. Okay? You can get max to max, you can get 2 or some fractions of each. So you may get 1.5 here and 0.5 somewhere else. So basically, if you remember on slide 1, I said scalability is, the previous slide we said we have to give a massive scaling platform, a massive scaling network. So Ethereum and Bitcoin do not fit in there. Scalability is right there, and we need something which can compromise a little bit on decentralization, but gets more on the scalability side. We'll talk about it. Okay. How many of you have some bit of understanding on blockchain, like proof of work? How many of you have heard about it, proof of work, ever in past? I think there are some people. Okay, cool. So what happens is, these peers are different people, let's say. Let's say peer 1 is me, it is my resources, my machines. Peer 2 is somebody else's machines. Peer 3 is Vignesh's machines, right? Now, all of us are taking part into a blockchain network, okay? If you look at the sizes of the box, they're intentionally done. Peer 1 is mid-size, Peer 2 is large, and Peer 3 is a tiny one. So Vignesh is a tiny one. He has probably a couple of machines there, not much, right? You need a lot of money to bring a lot more machines there. And peer one is me, so I'm like somewhere in mid-range, let's say with 10 machines. And peer two is somebody who has got 100 machines, right? So that's what this network is. This network is built of some 100 plus machines where 100 machines come from peer two, 10 from here, and 2 from there, right? But the problem with proof of work is it will say everybody will start performing the transaction together. All the peers, whenever there is a transaction which is given to the network, how does it come to the network? Again, your app, you will say, I want to make a transfer. So that transaction comes on the network. Now, when it comes on the network, everybody has to start processing it. Everybody has to start validating it. Everybody has to start block creating it and make sure that their block goes to the blockchain finally, the database finally. How will that happen? So the same transaction goes to everybody. They all validate it. They all perform their validations. And then they try to add it to their block, whatever the block they have. But after that, only one of them will succeed to add it to the blockchain. Others will not. Now think about it. If there were 1,000 participants, 1,000 peers here, and all of the peers are doing more or less the same thing, but only one of them will go through, the problem is, okay, then why did others spend so much money on their computers, on their electricity power, and all those things? What's a gain of it? It's not going to gain anything. So, but why are we doing it? So that's the problem with proof of work. In this, everybody competes. They all perform the transitions together. They all try to create the block. And to create the block, when they create the transaction in the block, the entire block of transactions, they try to hash it. They try to compute a hash, which is a specific value. And that's called a mathematical puzzle. I won't go into deeper details of it because a lot of people don't even know what it is. But that solving that puzzle takes a lot of time and effort and machine resource, electricity, everything. Which means all of these peers have to spend so much to get a transaction validated and to form the block, but only one of them in the end will form the block. All of them else will say, okay, fine, we lose the race. And the last thing that they do is, the one who wins the race will send his block to everybody else again and say that, hey, I have performed this transaction. Now my block is here. You also, and it will also send the algorithm. So basically the hash calculation that happens is a mathematical puzzle. It will not only give the block, it will also give the, how did it solve the puzzle. And then all other validators will run the same puzzle and say that, yeah, that's correct, that's correct, that's correct. When majority of the players say, yeah, you have done the right calculation, then only that block goes into blockchain. So there are so much of wastage, you can see. The initial creation of blocks was a wastage. Once the block is created, then again it has to go to everybody for validation that the block creation is correct. But all of that is to bring security, bring trustfulness in the system. So basically what you end up seeing is the chain replication happens here, no problem. The chain immutability is also taken care of. That is also no problem. But the top three, resource wastage, utilization happens when they are building the consensus, whether the block is correctly calculated or not. When it is sent back to all that part is called consensus wastage. That is also happening here. The scalability, of course, is happening because it becomes heavily sequential process. Now, then comes Ethereum kind of network where they said, okay, we won't do proof of work, we'll do proof of stake. And what a proof of stake is, it says, again, there are three peers, same, me, somebody, and Vignesh. And, what is stake here? So stake is like this. If, let's say, we three come to take part into the network, we'll bring some money, we'll keep it in the pool. So I'll bring 100 rupees, he'll bring 5 rupees, somebody will bring 1,000 rupees. So whoever brings more money, they will have a higher probability to compute the block. How will that happen? So think about it, right? Let's say I bring 10, so you create a ring. You create a ring, it's called a hash ring. So you create a ring. Whoever has brought in, let's say somebody has brought in 1,000 rupees, so you create 1,000 hash spots for that particular peer. Who has brought in 10, you create 10 spots. Who has brought in 5, you create 5. So you have 1,000 plus 10 plus 5 spots in a ring. You toss a coin or you just leave a ball there, just like casino, you leave a ball, no? The ball will rotate and finally it'll get to some spot. Now, who has the highest probability of that ball? Who has the maximum spots there in the ring? So what happens is, the more the stake you have, the chances that you will get to compute the block is higher and higher. Nobody is asking me a question like, okay, why do everybody wants to create a block? What happens? Right? So every time you are able to successfully create a block and append it to the blockchain, you're paid for it. And when you are unsuccessful, it's a waste. You don't get anything for it. Now here, same thing happens, a transaction comes, but then since peer 2 stake was highest, looking at the size, peer 1 and peer 3 are silently sitting and peer 2 has started creating the block. The transaction creates the block. Now when the block is created, again peer 2 will send it to all other peers, say that, hey, I have created this block successfully, validate whether my block is correct or not, whether it is rightly calculated or not. So these peers will again do the same calculation, prove that it is calculated correctly, and then finally this block gets into the blockchain. So if you see resource utilization, we have gotten better here because not everybody is doing the same thing. Only one peer was doing it. But consensus wastage and scalability issue is still there. This also cannot scale. Now let's see what was done next. So Ethereum brought another way of doing it. Okay, we need to further scale. What we do is, the next thing was, okay, all of us know about layered architecture. So you create multiple layers, distribute the responsibilities, let one layer do something else, another layer do something else. So there is maybe the parent layer. By the time things reach to the parent layer, most of the things are done, so parent layer has to done very less, and that's how you can scale it. Here also, if you look at the architecture, this is the main blockchain that is on the top. And then more blockchains were created, more networks were created at the bottom, and they were called side chains. So it's like this. Very simple analogy I'll give, maybe all of you understand. Hello, everybody with me? Okay. So very simple analogy. Let's say Paytm wallet nowadays is struggling, but let's take that example. So let's say you have a bank account. You transfer some money to your wallet, Paytm wallet, right? Now you go to the shops, you scan the QR code and keep making payments using your wallet. Will these transactions show up in your bank account? Will they? Have you tried? They don't. The only transaction when you transferred money from your account to the wallet was registered in your account. If you send money back from your wallet to your account, that will also be listed in your account. But in between, let's say you transferred 10,000 rupees to your wallet and you kept on spending it throughout the month, all those transactions are not registered in your main bank account. They are registered with another account, and that is the side chain here. So what you're doing with main chain and side chain here is, main chain has your main asset. When you want to transact a lot on it, you transfer that asset from main chain to side chain and then transact on that. Now what happens is, let me tell you, when you transact with these kind of blockchain networks, every time you transact, you pay a fee for it. There's nothing called free transfers like you see in bank accounts. Nothing is free here. So you make a transaction, you pay for it. You make a transaction on a busiest blockchain network, you make the biggest payment for it. You make the transaction on a fair enough little idle kind of a blockchain network, you pay less there. So with these kind of side chains sprouting around the main chain, what helps is they will say that, okay, bring some of the assets here, keep transacting on it, and you pay less. Okay, but they are less busy, but they are less secure as well at the same time. So you will bring some assets there. You will not, I don't think anybody would have brought in like 10 lakhs into Paytm wallet. People would bring 5,000, 10,000 to the wallet and then use it. When it is empty, you bring 4 more and then keep on using it. That's how you do. Similarly, these side chains are used. You bring some assets here which you want to transact further and frequently use the side chains. Very nice way to scale it. If you see, it's a beautiful concept, and this is where Ethereum 2.0 started looking for further scaling and some kind of scalability with an orange tick. Okay, we are reaching there. It's getting solved. But again, the consensus wastage will still be there because that consensus mechanism has not changed. Wherever it is happening in the same way. A peer which is finally creating the block will send it to all other blocks, all other peers. But our goal is to scale the main chain itself. We cannot survive with so many side chains. We can have side chains, but doing different kind of functionalities, not for scaling. And the kind of throughput we are looking for is 1 lakh transactions per second. If you want to do something like this in India, this is what you need, or even more because it is continuously growing. So we have already talked about this blockchain architecture. There are some apps, then there are some validator, and then there is a block creator in the end. If you see, there is a small change in the diagram. If you see, there are 2 clusters of validators. Cluster 1 and cluster 2. In the earlier diagram, we had only 1. So basically, the validation that you do is a stateless problem. You can do in as many parallel processing as possible. So all of software engineers know, right? Whenever we want to scale, we immediately try to find out what is stateless in my system. Because stateless things take time. Usually validations, they take time. But at the same time, they're stateless, so you can scale them in parallel processing as much as you want, right? But where the database, if you look at the database, if you go into the database has 2 things. One is it has a service. When you write select blah, blah, blah from that, right, from a table, it is doing 2 things. One, there is a service attached to the database, which is stateless, but then there is a storage in the end, which is not stateless. It has state. And that's where the database also finds difficult to scale. And that's where a lot of different kind of key value databases and NoSQL databases have also come out. So we'll not go into that. But to understand, in the blockchain also, the only component which is handling with the blockchain is the block creator. But the validators who actually validate the functions who take time, they can be scaled. So that was a nice finding that, okay, fine, there is something which is horizontally scalable in this system also, which we can probably take a look at. But we were very clear that, sorry, that piece is not going to scale. That is not going to scale, no matter what we do. So we have to find a different way. And that different way is very well known to all of us. All of us are very familiar with it, and that is called sharding. How many of you have used partitioning and sharding in databases? A lot of people. That's the only way to scale it. I mean, beyond a point, you start sharding and scale it. If you have used Kafka, for example, Kafka's storage also scales up to a point, and then it reaches a point where you need to shard it further. One cluster does not go beyond it. Even number of topics you can create, there is a cap over there. Now, all right. So, okay, fair enough. So what do we do? Because we still have that one problem, scalability. How do we solve it? And we said that main chain and side chain business, it's okay, but for a different use case, not to scale the main chain itself. The main chain has to scale. And if you see, it says with trusted peers. We are not talking about proof of work or proof of stake here. We are talking about, okay, if we have trusted peers, what happens? And Mr. Anil has already talked about a lot that if you look at India, for example, or any other country, the peers must be trusted. And so for example, if there is a banking domain problem, then bankers have to come together as peers and solve that problem. If there is an insurance problem to be solved, then insurance players come together and try to form a network. So these networks cannot be permissionless or without any criteria. So criteria is that if 5 big banks of a country come together and try to create a network, then we trust those banks. They have a lot at stake. They don't have to bring money and keep it on the table. Their whole brand, their whole reputation is at stake. So they won't do wrong. In proof of stake, money was to be brought in because we know that, right? It was permissionless. Now, with trusted peers, what happens is every peer is equal size. Now, no more Vignesh, Manish, and Anil business. Anil was rich. He was bringing 1,000 machines so far. But now, no matter how many machines you bring in, from the stake perspective, we all called same. And when we all called same, Um, just one word. If you want to distribute this transaction between these three, let's say, what will you do? If they all are same. Huh? Round robin, somebody said. What else? Everyone, then the problem of proof of work will come because then everybody has to do the same thing. We don't want to do that. We want to do only one at a time. So round robin has a problem because whenever you do round robin, you can predict who is next. Hashing is another way. Hashing is another way. But consistent hashing also has a predictability. Maybe on the transaction ID, you will create a hash and then see where it fits. That's also predictable. If your one kind of transaction will always go into one peer. What else? Random distribution. See, such a simple thing, right? Anything which is predictable, you want to make it non-predictable, you randomize it. So what you do, a block has many transactions, right? It's not per transaction a block is created. So the peer 1, peer 2, peer 3, they toss a coin on a random this thing. They decide who will open the next block. So whoever is opening the block will close the block, put it in the chain, and then the toss happens again, who will do the next block. Simple, right? Very simple. So now what happens is, the transaction peer 1 opened the block already there because the toss went in its favor. The transaction 1 then goes to the block from peer 1. And now, if you see so many green arrows now, right? Resource utilization is pretty good, no problem, only one of them is doing it. Now the important thing is consensus wastage. So far, if you remember, in proof of work, proof of stake, Ethereum 2.0, even though you could scale it, the next thing was when the block is formed, that block was transmitted to everybody else to do a final consensus whether the block is correct or not. Here, since we trust all the peers, we can do that part retrospectively. We don't need to do it proactively. So what we are saying is, hey, you know what? You append your block to the chain and we'll keep on validating the chain little lagging behind, but there is a service which is continuously validating the chain little behind from where the head is at any point of time. Okay? So they can go ahead and immediately add this block to the chain, which means, now think of it, it's just like any other software service, isn't it? That you have written in past. You send it a transaction, it'll validate it, it'll put in the block, just like a database, append it in the blockchain. Everything is like one shot, single atomic transaction, right? And which is very fast now. And the other thing now, the remaining thing is, okay, what about scalability? You talked about all these things, but scalability is still there because it's only one peer doing it at a point of time. What other peers are doing is sitting idle and waiting for their turn, for the next toss. And these machines are on. They are always running that service. Think about if you are running a service in AWS, even if you're not building any blocks, if you're just sitting idle, your meter is running, right? The payment is always happening. What do you do next? As I told you earlier, we have sharded databases. We shard the blockchain itself. And if you look at here, take your time, observe the diagram. It's not very difficult, it's very easy. There are 4 peers in this diagram. Peer 1, peer 2, peer 3, peer 4. These 4 peers bring in some kind of capacity to the network. If you see, the network is all with those 2 white background boxes, shard1 and shard2. That is the entire network, as an example. Peer 1 brings 1 machine there. If you look at peer 4, it is bringing 2 machines, one in shard1 and one in shard2. Peer 3 is also bringing 2 machines. Peer 2 is again bringing just 1 machine on the green side there, right? So different peers can bring different capacity to the network, but then network is sharded. Now when network is sharded, every shard is a separate blockchain. Okay? What it means is, I will not let 100 peers join one shard. I can limit how many peers can join a shard, so that let's say 5, 7, 10, some limitation there. And so you form multiple, you keep on forming so many multiple shards. So when new peers are joining in, you create a new shard. You create a new shard like that. Now, the question comes, all right, okay, blockchains, let's again rewind back a few steps. How does blockchain work? How do banks work? We all have bank accounts in bank. Similarly, in blockchain networks, we have got wallet addresses, which are equivalent to accounts. And these wallet addresses are there somewhere in the blockchain, and they have a connectivity to the blockchain. So if you do a transfer, it knows how to do that because that address is available there. And the address you are transferring it to is also available there. So when from and to both are together, the transfer can happen, right? This is old age problems. You could transfer only from SBI to SBI. Do you remember that? And new generation will not know that. But there was a time when you can actually transfer from an SBI account to SBI account, from an SDFC account to an SDFC account. You could not do a transfer from SBI to SDFC. Why? Because these two accounts lie in two different platforms. They have no connectivity with each other. And then we brought the connectivity, and so more and more transfers could happen across banks. Similarly here, the same problem can happen. These are two different blockchains. We are calling them sharded chains, but they are two different blockchains. And they have totally different database altogether. So the possibility is that the remitter account, the one who is transferring the amount, is in shard 1 to an account which is in shard 2. And then how does that happen? To do that transfer, the blockchains are not supposed to go outside. But here we need to build that, and in a very secure way. And what happens is shard 1 creates the transaction as a debit transaction, let's say, which goes into shard 1 blockchain. Then that particular transaction, the second part of it, which is a credit transaction, is given to a shard manager. Shard manager knows where is this beneficiary account is, in which shard. And then it will forward the transaction to that shard. And that's how that shard will execute the second transaction, second part of transaction. And that's how the entire transaction completes. All right. Does it make sense? Does it make sense? Huh? All right. So now all green arrows, we have scalability issue just got resolved, because now we can have as many shards as possible, and we can resolve the scalability as long as we can do this inter-chain reactions. So from chain 1, something happens, goes to chain 2, to chain 3, to chain 4, and this reaction should be, this entire trail should be possible. If we can make that happen, fine, we have achieved the solution. And yes. I'll come to that. Yeah. So this slide will answer a question. So there were multiple ways to shard the addresses. Now these accounts, they have to be sharded in some way. One was use consistent hashing of addresses and shard them, put them on some shard. The other was by creating a map of address to a shard number. So you say this address or this account belongs to this shard always. So you keep those kind of mappings. If you do the hashing of addresses, the main problem happens is whenever a new shard is added, these accounts starts moving here and there. Because now, whenever you add new shards, the address may fall into next shard. It's a hash. I know whether you may not know about how does this hashing algorithm works, but if the shards change, the addresses can relocate into a new shard. That happens. And when you relocate the address into new shards, all the data that they had on one shard has to be moved to the new shard as well. Because if you want to make a new transaction, all the historical data must be present. And that's a lot of overhead. That's why there is a red mark there. And the other one was creating a map of account addresses to shard. Now, the shard manager that we saw in the previous diagram has the mapping of every account address to a shard. And that can be moved only when shard manager needs to do it. And so what happens is, even if you add a new shard, new addresses will move to the new shard, not the old addresses. And only when the shard starts filling up, when you are in need of more shards, you go back to your peers and say that, hey, people, we need more capacity, and all of them add one more machine in their data centers. So they add one more machine, and those machines put together form a new shard. So that is how the second one makes it easier, because now with shard addition or subtraction, added or removed, addresses do not move. Only when a shard is removed, addresses will have to move, but then shard manager will have a mapping and it can recreate those mappings. The other benefit that you get out of that is, it's a real world, right? So there will be always some accounts who do many transactions, very voluminous accounts. And if one shard happened to get many of such accounts, it becomes a problem. That they will get more busy rather than other shards will just be idle and sitting, because the accounts lying there are not doing much. So Shard Manager is basically, it's an AI-driven service, which is continuously looking at the transactions retrospectively and finding out where are the hotspots, which shards are into hotspots, and will try to move these accounts into the shards which are not doing much. And that is the way it keep on. So whenever there is a movement, the entire data is not transferred. We figured out a way to transfer the data also, where the entire data need not be transferred, let the data be there. We create a hash of the entire data which was created in one shard and put a signature element on the new shard. That way you tell that this has a tail somewhere else, and that address is also stored. So in case you need to go back and check the entire tail of the transaction, you know where to go, where is my previous data. So in blockchain space, I think a lot of people think that blockchain is the only database they have. That is not true. Have you seen event sourcing systems, event-driven systems? Just if you can just quickly let me know how many people know event sourcing. Event-driven, not event-driven, but event sourcing. Okay, very few. So event sourcing systems, what happens is you record the event first. So let's say there is a credit transaction. You record the credit transaction first, and then the effect of that transaction is stored in a view, which view is used for your all other further needs to display your account balances on the website, etc., etc. But you do not, to show your account balances on your website, you do not go to the event, the actual events which happened. Similarly, here also the blockchain is not for continuously querying. Blockchain is just immutable record keeping, so that in case of audit, etc., you can go back to it. Every time there is a new block or a new transaction, the transaction is put in a state database, which is just like Postgres database or any other database that we have seen. That database is used. So here, even if my data moved from one shard to other shard, it was fine, because my state database will still be there. And do I have time? How much is done? 5 more minutes we have? Okay. So just now, I think I have dipped you in a lot of depth there in terms of how it works. There's a lot, it's not easy to convey. When there are people who have some understanding, you just build on top of it, becomes easy. I've tried to keep it very easy for you to understand how we arrived from one kind of architecture to a derived architecture, what worked for us. But look at the use cases. Mr. Anil has already talked about many use cases. I'm just talking about how it works. This is very simple. Just pay attention again, and nothing linked to the past, whatever we have gone so far. Fresh from here. Okay, a couple of slides. So we already have CBDC running on a DLT network. It's existing, right? Which means that there is some digital currency available in the market running in a DLT network. All right. Then we wanted to create a network of loan givers, and they can give loan based on a lot of factors, but this is against collaterals. So you have, let's say, a house property or something, you go and put it as a collateral to the bank will give you a loan. This happens, right? It's very normal, right? You keep your property. Even mortgage loans are similar loans, right? You keep your property papers with the bank, and then bank gives you a loan on top of it. And then we have real estate registry platform. This is something we do not have, right? Now, if you want to get a loan, what do? Again, you will take your property papers from your locker. You will take it all the way to the bank. You will keep it as a collateral. Bank will keep it in some locker, safely keeping it for 20 years, making sure that rats don't damage it, and et cetera, et cetera, et cetera. It has big responsibility to keep your papers safe. And then, these papers, how much value they have? A lot of people are using DigiYatra nowadays, right? If you go to airport, they'll scan your face, and then they'll say, okay, show your DigiLocker identity. Your Aadhaar card must be in DigiLocker, then only they'll accept it. They'll not accept a printout. Why? Because DigiLocker gives guarantee that your document is tamper-proof, it is real, and this is just one copy of it. But when you take your property papers in physical form and keep it with the bank, I don't want to say that, but isn't it you can create those papers again? It doesn't happen. It never happens. I know that. But people say it happens. So I don't say that. Here also, if that can happen, then you can actually go and procure loans from multiple banks on the same property, if you could do that. And there are people, if people say, maybe there are people who could do that, but who is losing in the end? It's retailers whose money is being lended to these people. They are at the losing end because banks make a mistake. They consider those papers as the only paper possible for that property. A problem. And that's where you would have heard very recently, the entire property with their lat long and coordinates is being digitized in India. So every property must be a digital signature. Which means that it's only one, and you cannot produce second one. And once you have that signature available, you can take that signature, and if that signature is available in your wallet, the wallet of DLT platform, like any other wallet, if you have that signature present in your wallet, then you can go and produce that, hey, here is my wallet, here is my asset, give me loan against this asset. It becomes very easy. Banks won't ask you to go to a notary and all those problems are solved, which means that one bank, one loan, one property. The other thing that happens is all of these are interconnected using some black arrows there, and these are called asset bridges. I don't want to confuse with that, but think of them as another set of services which connect the two, right? So whenever we have aggregators, for example, you have multiple airline booking ticket sites, and there's an aggregator on top of it. So these are they are like aggregators. They know how to aggregate these two networks together. So you kind of put your real estate property you block that property in one of the network. It's called pledged. And once it is pledged, you cannot use it again for any other loan or in their case. That's possible with, oops. The only thing, how these can network with each other, different networks can network with each other, is only possibility by standardizing their contracts. You cannot keep writing contracts. Right now, all of us, when we write one service, and we need to transfer data to other service, we just give contract to that service. Hey, take the contract. That service writes it. Then you need to give to some other service. You give another contract. And that's how contracts keep on growing. And we are stuck with so many contracts who are not standard. So standard contracts, standard specifications, standard protocols, and then only you can integrate this. So quickly getting over that for developers, I have mostly talked about all this. I'll not go into that. But look at that. Ethereum brought in these two contracts, ERC20 and ERC721. These are token contracts. So anything and everything you see, chair, table, fan, light, doors, property, diamonds, jewelry, whatever you see, any object can be tokenized. And you can use ERC721 kind of token contract to define that asset and put a signature on top of it. ERC20 is mostly used for things like currencies, etc., because you can replace one 10 rupee note with another 10 rupee note, doesn't matter, right? So for them, ERC20 and 721 when you have specific and unique assets. For developers, it's not rocket science. It's very easy. This DeFi space, it feels like it's very difficult, it's very complex. It is not. This is one, it's just the same ERC20 token which Ethereum has written. I've brought in here. If you look at it, it's very simple. If you have, let's say, use Java, here you have some of the class level variables defined. Here, some of the contract events defined. So if this contract is run, it can emit these events during performing different actions and functions. Then you have a constructor, and then you have functions defined here. I have kept it very simple to understand. So function says transfer from my address to this address, and that is the value. What is the amount that you want to transfer? It's as simple as that. You do this transfer here, and in the end you say emit transfer event. Which means that once this transfer is complete, you emit that event. And anybody who's interested to know about that transfer happened can look at that event and take it further. Similarly, there are other functions like approve, transfer from. Now, these are the functions defined in the contract. There are more functions here. And one of the functions says, how can you spend this money? Whether you can spend it on this merchant or that merchant. A contract is there, but you can implement it the way you like. So understand, this is just like an interface, and do the implementation. Very simple and straightforward, and what a transaction looks like, it's something like this. I think time is almost over, so I'll not go detail into it. But that's pretty much, you can connect with me over LinkedIn. How was it, guys? Looks like people did not chill out much today. All right.
Signature was very interesting.
Okay. Thank you.
Yeah.
Sorry? Yeah, please give a mic. Yeah.
You provided various architectural patterns, right?
Correct.
Is there any ready-made library or anything that is available for one to?
So yeah, I think that's a very good question. So for all the developers, there is a packaged software from IBM. It's called Hyperledger Fabric. Maybe that could be a good starting point. You can start with that. You can put it on your machine. In one laptop, you can start working with it, and that will give you a good grasp of all these concepts. And you can actually build a network on your machine itself. If you can work with Kubernetes and you can bring a few pods together, maybe you can create a network on AWS, a small network, and see how it works. This is very easy. It's the same technology that we have seen so far. This is no different. When I started doing it, I was very nervous. But then when I looked at it in little detail and get into depth of it, I realized that, hey, it's no different. This blockchain is just it's just a fear, it's just a barrier that we have in our brain, in our minds, but it's nothing. You can, if you know how to write software, you can write this also. Yeah.
What if we hacked the private key of the address here?
Hey, so one more thing. I would ask organizers to tell me if I can answer these questions now or we want to take it later.
So we have a dedicated time for asking questions. Probably we can take this up later because
Okay,
we have next
sure.
interview.
So we can meet during dinner also? Okay. Yeah, we can talk. Thank you.
Thank you, Manish, for demystifying the tech side of decentralized finance and showing us how it's all coming together. Thank you for that. Okay, that can happen. We can have it in dinner time. Okay, now as we are going to enter into the last set of event, the fascinating field of AI. So, Venkatesh will now delve into the fascinating realm where artificial intelligence converges with decentralized finance. So, we will also be looking at the unlocked precedented opportunities. So, he will also emphasize the potential spaces where AI LLM can be used, and in the analyzing the transactional records and identifying the potential risk and also the challenges and future things that can be coming up in the process. I would like to call upon Venkatesh for setting the stage.